So today we're going to be talking about electric fields, which happen to be one of the most, if not the most important concept in molecular biology, because electric fields in some way or another determine almost every single atomic bonding event and almost every single molecule and almost every single form of life that's possible in molecular biology, in organic chemistry, in any of those fields, even though it comes from a completely unrelated field of physics. So let's learn about that today. So the main thesis behind electrostatic attractions and electric fields revolves around the fact that certain subatomic particles, or the particles that make up atoms, have a property called charge. Now, charge isn't something we can see or feel or really understand in a real way, but charge can be best understood by observing how charged particles interact with each other. And you probably know this best by the rule that like charges repel, unlike charges attract. So things like protons and electrons, charge determines how they function in a very useful way. But charge is still very unintuitive to understand because we can't see charge. So let's try bringing charge up into a different analogy, which is the analogy of gravitation, which is actually acting in a way that we can see. So imagine we had two planets floating around in space. And I guess the question I can ask you from here is what makes two planets or two objects with mass in general attract? Well, the answer, at least according to classical physics, is gravitational fields. This is the spooky force that acts between planets and lets them attract without even touching each other. This is the entire concept of gravity, and it's explained by these mysterious fields that are created around planets and, again, any object with mass. So we have this large planet over here. It creates this sort of field around it. Now, this dotted notation doesn't do it justice because a field is more like a gradient, and it's actually much stronger near the surface of the planet, near the edge of the planet, which makes sense, of course, because that's just how gravity tends to work, just like sound or light or any other physical phenomenon. It's always closer and more stronger at the source than far away. So we have gravitational fields interacting with each other, and that's how planets attract. And in fact, we could carry this over to another more real world example, which is, let's say you had a ball and you wanted to drop it to the ground. Well, the ground is Earth, of course, so we had a planet that's like round here. Now, it does look flat in this context because the Earth is so big, but you can imagine that the ground also has a gravitational field of its own, and it's very strong at the very surface of the ground, and it gets weaker as we go up and fainter. But this ball also has a gravitational field. Now, imagine what happens when this ball is dropped and it's allowed to reach the ground. Now, at the beginning, the ground's going to exert a slight pull on this ball, but as the ball gets closer, these two fields are going to get stronger because the surface of this ball, which has a strong gravitational field, is going to get closer to the bottom of this ground, which has an even stronger gravitational field. And so you'll have the ball getting pulled slightly, and then pull slightly more, and then more, and then more. And then what you'll end up seeing is acceleration. The ball accelerates towards the ground because these gravitational fields are much more strongly interacting as the ball gets closer to the ground. And this is exactly what we see in the formula for the strength of a gravitational field, which is described as the mass of one object and the mass of another object divided by the distance squared times some constant. Now, the important part we need to look at here is the distance squared because, of course, we know that gravity depends on mass and all, but the interesting thing is how gravitational fields behave over distance. And we see that as distance increases, the strength of our gravitational field is going to decrease because, of course, after we raise distance to an exponent, this is going to be a larger denominator of this fraction, and it's going to make our overall value lower. So we see that gravity behaves in this exponential manner where it decays over distance. Now imagine how this carries over to electric charges. Now, it just so happens that the concept of fields is very generalizable, and it's such a useful toolkit to have in your arsenal because you can apply it to many other properties. Now that we know how gravity and gravitation works in general, we can actually transfer this analogy over to electric fields, and it would be 99% the same. It would be very, very similar. The only caveat to the situation would be that electric fields have this property that makes them slightly more complex than gravitational fields, and it's this concept of polarity. So the easiest way I could explain polarity to you is that for any object with mass, if we look in the context of gravity, we'll have this pulling action towards this object's center of mass, because this is essentially the source of its gravitational field. We have this pulling action, and regardless of the object, we'll have this pulling action. Whereas in electric fields, we have certain particles that behave differently. Their fields have a different directionality to them. Some have a pushing nature, while others have a quote-unquote pulling nature. So in fact, we can describe this in what we call field lines of certain charged particles. So in the context of a proton, we would have this outward pushing nature, and for an electron, we'd have this inward pulling nature. Now, you're probably wondering what this is in the context of, and by convention, we draw field lines in context of if there was an imaginary proton right next to our particle. So if we had a proton and a proton next to each other, of course, we would have some repulsion going on, and this makes sense because this proton would also have the same field lines as this proton, and you can imagine that if two people push each other, they're going to both get separated by a distance. Now, on the other hand, we have an electron, but this time this is also in the presence of a proton. And since a proton has this pulling action, this pushing action attached to it, and its fields have this sort of directionality, these are actually complementary in nature, and if you put them together, protons and electrons will attract as a net result. And this is where the saying comes from, opposites attract, at least in electrostatic attraction. And this is sort of the finalized diagram of what would happen if you put two unlikely charged particles in a room together. And you'd see that this pushing nature of a proton sort of couples with the pulling nature of an electron, and the net result you get is an attraction. So whereas if you had a proton and a proton, it would be like two people pushing each other away. A proton and electron would be somebody pushing you and you pulling them in closer. The net result, of course, being attraction. Let's see if I can spell correctly today. Attraction. And as you can see, these fields behave in a very similar way to gravitation, in fact, because electric charges and electric fields are stronger near the surface of a charged particle, and they get weaker over distance. They decay, they dissipate over distance. Now, as you can imagine, there is a slight interaction. If you keep these particles far apart, there's going to be a slight interaction because their fields are weak over here. They're weak. But as they move closer and closer, as they move closer and closer, their fields are going to get stronger and stronger because you're closer and closer to the surface of these particles. And what's going to happen is you'll have the same attractive force, and these particles will go faster and faster towards each other until they get as close as they can, physically possible, to each other. And in fact, we describe this in essentially the same bare bones formula as the formula for the strength of a gravitational field, which is an electric field strength is defined by Q1 times Q2, which is the charge of both particles, over distance squared. So this also decays with distance times a constant. But overall, this is how particles interact. This is how charged particles interact. They accelerate towards each other, and eventually they stabilize. And we'll understand why this stabilization event is so important when we cover the concept of potential energy. But for now, I hope this lays a great foundation for you to move into more complex topics. Thanks for watching.